Okay, first one up is welcome to Block 7. Objective 1 Alpha, identify basic facts and timing about synchronization standards. Now, with this particular test, oh my goodness, it is 40 questions long. That means you have to score or get correct 28 questions. You can only miss 12. There is 2 TOs, or a tech manual and a tech order, some electronic C's and D's that you will have available to you. They also have paper C's and D's if you request them. So just letting you know, those are coming with the test. So you have that to fall back on. And I'm going to tell you right now, I do go through the tech manuals and the tech orders to give you the highlighted versions of where you need to focus on in both the labs and the test and homework and appraisals. So it's a combination of everything here. The idea is to be so familiar with this stuff that when you walk in, you're going to do really well on the block test. So that gives you an idea of what we're looking at, what the requirement is. There is the AFSC application. You're going to be dealing with time. Okay, like everybody does, you know, you're supposed to be here at 10 o'clock. That's time. You're going to see a lot of different variations on the time. You're going to deal with equipment that requires time. So let's take a look at the overview here, which is the purpose of timing, timing standards, timing sources, time coordination to distribution agencies, the timing jitter, and network synchronization. You're going to notice that I will go fast through some and slow through others. That's a hint. Purpose of timing. The big thing is, with all of our equipment, it relies on synchronization. If our equipment isn't synchronized, we have issues. This includes like all of our SATCOM gear, radios, you know, things like that. You guys have already dealt with time. You probably didn't realize it. Besides, you know, what's on time on your watch and stuff. But you remember time of day back in Block 3? Yeah. That requires a timing sequence to be very accurate at that point. SATCOM terminals rely on time. Your internet relies on time. Pretty much anything that relies on technology relies on time. Here is an example of how timing works with the multiplexer. Just gives you an overview. You have all of these things coming into something called a multiplexer. Things like a nipper net, a sipper net, the local switchboard. Look at the amount of users on just those 3. And then you see some that are single entities like VoIP, Voice over Internet Protocol, or your computers, and you know, those are single entities. But when everything comes out of this multiplexer, it comes out in a stream of ones and zeros, along with what we call clock cycles, in order to make sure that our timing is in sync. You know, bye, in sync, bye, no, bad.
I thought it was hilarious, sir.
Oh, you're the first ones to catch it. Normally it's that. I can't believe he just said a pun. Okay. Anyway, just, you know, everything's in sync. So we look at the time standards and how things get developed in order to make things sync up. So we got apparent time, mean solar time, atomic time, coordinated universal time. So let's take a look at each one of them. Apparent time, that's earliest. Basically, it's the sundial. It is not very accurate. Why is it not very accurate? Because every day noon changes if you look at that sundial. One time it's dead on, and the rest of the time it's nowhere what the original time should be. You also have the Earth's rotation. It is an elliptical orbit, not a circular one. Elliptical meaning it's like an egg. Its axis tilt in certain seasons, like for example, we just had the summer solstice. And like I said before, it's the least accurate time. Then we get into something called the mean solar time. Now, this one is where we started developing mechanical watches and clocks and things like that. And I always like to refer to Big Ben. But when we were developing, I shouldn't say we, but when the English, the Spanish, the Portuguese, the Dutch, French, so forth and so on, they actually were able to develop timing standards in when they were sailing the ocean, and that's how things started to progress, and they finally realized, hey, there's X amount of time in a day. Now we got to figure things out. Now, what they did do is they developed what's called the prime meridian. Okay, all these scientists, and it goes right through a place called Greenwich, England. We call that Greenwich Mean Time, and also UT means universal time. So you're going to hear a couple different names for that prime meridian, or the zero line on the Earth's latitude. Then we get into more accurate timing, called atomic time. So GMT is considered the world standard. The atomic time is what it's referenced to. It is the most accurate that you can develop. So you're going to see GMT referenced a lot, but you're also going to see something else change from it. We have something called UTC, which is pretty much the same thing as GMT. They just like to call it different names, just like the Air Force likes to do. They like change for some reason, and everybody's flexible. But I always say, just wait about 5 to 10 years, it'll change back. Just a different name to it. This one is UTC is no longer the world's time standard. No kidding, because they changed to UTC. You have the Universal Time and Time Agency International. So all of these are referenced to atomic time. You'll see that it's referenced to within 1 millisecond. Oh my goodness, it's really quick. There are 24 official time zones, and you'll notice that I've got a link in here, and I suggest very highly that you go to this link because it is pretty cool. There is a lot to this, but I'm going to just show you the time zones here in just a sec. So we have Keesler Air Force Base, we have local time, but we always reference the UTC time, better known to us as Zulu time. So if you have a place that you go to that has missions all the time, you will see two clocks that will appear. You'll see the local time, and then you'll see Zulu time. All the missions in the militaries reference to Zulu. Zulu is the same thing as the zero line, UTC, GMT, whatever you want to call it, but the military always reference that's the Zulu time. This is, let me do something here. I've been meaning to do this to this particular map. Let's crop this bad boy and give us a little bit better view. Too much. Okay, can everybody see that?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Excuse me. These are referencing the timelines we have. The zero time frame is right about here, right in that line, right as it goes through Africa, Spain, England, part of France. So this is what we call the UTC, this little time zone in through here. You'll notice that there's some differences that's happened in there. You have one timing, which is one particular color, and you have different colors that are in there. Now, this is referencing to what the UTC is going to be in that particular area. Now, let's just look at the United States and focus on this one first. You have the green area, which is all of Eastern time. You have the yellow, which is all of Central, and the orange, which is Mountain Time, and then of course you have the West Coast time, Pacific time. Then you have Alaska time, and then you have Hammer time. You know, dun 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 dun. No.
Yes, sir.
Another classic.
Yep. Anyway.
I wish I had my soundboard.
Killing it today, sir.
Hey, if you don't keep it jovial, something's wrong, you know? So, you know, you can see the different time zones and so forth and so on, but there are some caveats to it, like the countries, they don't want to do certain things. Like, for example, I point to Australia, bottom right-hand side of this map. You'll see one of the time zones has diagonal lines in it. Those are half hours. Same with India. Looks like Iraq does it. Looks like Afghanistan does it. But take a look at China. This particular country covers almost it covers 5 different time zones, but it only has one time that it's referenced. So you can see it dictates, you know, they're still referencing the time to Zulu, but at the same time, they're going to make their own time. You come to the United States, I think Arizona doesn't even recognize Eastern or the daylight savings time. You got certain cities, they want to be outside of the timeline. For example, I know Louisville, Kentucky is in the Eastern time because they don't want to be in Central time, and so forth and so on. There's little cities and, you know, counties or whatever you want to call it that, you know, they have that little divide there. So it just gives you an idea. So we look at other timing sources, and the idea here is with this particular paragraph, it's saying that you have a primary source and a secondary source. Now, the idea behind the primary source is what you're referencing it to. You always want to be with the most accurate one. But on occasion, you might have to use the least accurate one to take the most accurate one offline and put it back online, so that way you have a reference. What can we say with this particular paragraph? Well, if I tell you we're going to have a break here at 10:25, you look at your clock and you say, or your watch, and say, well, no, that's not the right time. Guess what? My time is now the primary time, and your time is a secondary time. Well, if I take my, you know, what I'm looking at on my computer here, and I pull out my cell phone and I look at the time and I say, well, gee, my time doesn't match my computer time, so this just became the primary standard now. But you still want to get the most accurate for your primary standard. Will a secondary be the most accurate? Yet is very possible, because there is that little thing of back in the day, how did we get from being least accurate to most accurate? Well, we had to rely on a mechanical watch to get to a quartz. We had to go from a quartz to atomic time. So at one point, these were primary standards. But anytime that you want to do a primary standard, you always want to try to have the most accurate. Will the least accurate be it? It is a very good possibility, but normally it's for a short duration. We have two different types of We have two different types of timing sources that we use out there nowadays. It's quartz and atomic oscillators. First one is quartz. Quartz is the least accurate. It uses something called the piezoelectric effect. What that means is you're taking a battery, and this is mainly your digital watches, and you're exciting that quartz to a certain frequency. The frequency is taking hold. It's being as accurate as it can be, but there are two factors that create problems for it later on down the line. First of them, it's temperature, and then you got aging. The only one out of that you can control is temperature. Our atomic oscillators, however, are freaking accurate. We have two types, rubidium and cesium. The rubidium one, I have had the luxury, I guess you could say, of using it. It is a very accurate source. We used that particular timing sequence when we were using the 206 palette, which had 4 radios in it, and we did a lot of frequency hopping with it. Cesium is more accurate, though. As you can see, rubidium, definitely more accurate than a quartz. Cesium is more accurate than rubidium. We do have these up in the GPS satellites, but there's a new kid on the block that I just found out about 2 or 3 months ago that is starting to replace all the atomic oscillators. It's still in atomic oscillators, but it's more accurate than rubidium. Gee whiz stuff. Time coordination. So with all this accurate time, we need an agency that's going to generate the reference time for the world. It determines how many, in our case, events, or 86,400 seconds in a day, and that appears to be the standard for the world. We have the distribution agencies which distribute this accurate time. The main agency is BIPM. And you'll go, well, International Bureau of Weights and Measurements does not equal the acronym BIPM. It does. It's more of the English version than it is the French version. We also have DoD version, which is USNO, and then we have the civilian version, which is NIST. USNO and NIST get their time from BIPM. BIPM is the holder of time, and it is also the reference for how accurate you want to be with your devices. In other words, scientists normally ship their equipment to BIPM, they calibrate it and send it back. Why? Because they are the place where everything is referenced. In other words, time is referenced there. Your weights and measures are referenced there. For example, we're on the imperial measurement system. They are on the metric system. So you got to have like pounds versus kilograms, things like that. What's a centimeter as far as measurement? What's an inch as far as our measurement? So those are things we calibrated against. Weights and measures. And also your scientific gear is calibrated from there. So they provide a reference and they send it to you and you can reference off of there. So it's kind of like the PMEL lab. They're the ones that make sure that all of our equipment is very accurate. Why? Because they're referencing to another piece of equipment. For those of you that know what a PMEL lab is. That's our equipment that we calibrate, like our SIGGENs, our spec annies, and so forth and so on. Anyway, this particular time coordinating agency is out of Paris, France. It maintains the UTC, Zulu time, whatever you want to call it, GMT. It has many different atomic oscillators to keep a accurate time for the world. Now, if you ever go to this organization, you can see the link down there. It will look something like this. Up in the top left-hand side, let me do this. You can see the Bureau International des Poids of Mesures. I'm not very good at French, so take it with a grain of salt. But it just gives you an idea of what we have as far as BIPM. You can go to the right-hand side where it says meteorology area, and again, this is the link. You can look for acoustics, ultrasound, and vibration. You can see chemistry and biology, electricity and magnetism, ionizing radiation, length, mass and related quantities, photo, whatever it is in radiometry, thermometry, time and frequency is where we would be most interested in, and units. So that's one place where the timing is being kept along with everything else. Then we have the USNO. This is for the Department of Defense. The big thing here is the headquarters is in Maryland or DC, depending on where it's at right now. They keep going back and forth. But where they keep the time is down here in Pensacola, at the Navy base where the Blue Angels is. You can see that on this particular slide we have a phone number. If you were to dial that phone number, when it picks up, normally it takes 2 to 3 times for it to pick up, you can get the UTC time and you can get Eastern time. So if you want to impress your friends, there you go. Again, this is recorded so that way you can go and take a look at it. Also, the USNO has a website. There it is. It has a lot of history off to the left-hand side under USNO. Highly suggest that you go and see it and peruse through it. Next one is the National Institute of Standards and Technology, NIST. This is something that you could possibly have used when you went out in Block 4 if you had the radios. Did you guys have the radios out there? No?
Yes, sir.
We did not use the radios for Block 4, sir, for assembling the antennas.
Oh, okay. Well, when you did, normally there's not only can you communicate with them, but there is the primary radio stations for time. This is time hacks, normally on the 2.5, 5, 10, 15, and 20 megahertz. And last time I was there, which was back in April, they had those programmed in. So if you were having problems, trying to make communication, by going there and being able to receive them, you knew that your receiver worked. So that's one way to use it for not only for time, but also to see if your radio's working. They have 3 different call signs. One's WWV. That's where the headquarters is. WWVH is in Hawaii. WWVB is in Boulder, Colorado. You can actually tell the difference between Boulder, Colorado and Hawaii. How do you do it? Well, male voice, Boulder, Colorado. Female voice, Hawaii. Has a lot of history to it. Look it up. Also, there is a phone number in there. Every 30 seconds, it'll give you UTC time. On occasion, if there is severe weather, like a hurricane or tornadoes, it will also come over the air and let you know what's going on. Things like the wildfires back in California, the hurricane that was in Bermuda, things like that, they will update you to a certain extent. You can hear these things throughout the world. So not only is it in the United States, but you can hear it in the rest of the world. It is very possible, and I've heard this twice since I've been here, so it's a very unusual occurrence. You can hear both the Hawaii and the Boulder, Colorado at the same time. When I mean the same time is, believe it or not, in Hawaii we heard first, and then came the Boulder, Colorado one. So there is some time lag to it. Crazy. This is what the NIST looks like. There is a history section in there. Suggest very highly that you go through it. Just to peruse through it. It's not a requirement, for going through these. I like the time and date better than I like anything else. Why? Because it has like elliptical time frames. Elliptical. Excuse me. What do you call those things when the sun gets blocked off? Eclipses. There we go. It has a list of when the next eclipse is going to be, whether it's a solar one, whether it's a moon one, or, you name it. There you go. Timing jitter. This one is a fun one. It is an undesired shift of data or clock cycles. What does that mean to us? It means that if you're watching your YouTube or Netflix, you ever notice that little circle comes on? That's a timing jitter. Why? Because it's trying to sync everything up and it's not working very well, especially on YouTube. What will happen is, depending on the technique that it's using, you have short-term and long-term jitter. Mostly the Netflix and your YouTube is your short-term jitter. Why? Because it wants to put it into a buffer to where it gets enough information that it can judge by the amount of information it's receiving to play the video and audio at the same time. There are some times though where, for example, if you're at, if I'm at work and I'm on a YouTube video in the afternoon, hang it up. The chances of me being able to play that complete video at, all at once, very slim. Let's take a look at each one of them. Short-term jitters, small glitches, so to speak. Nothing is worse than you playing a game. How many in here play? Well, let me ask you, who doesn't play an online game? Well, I shouldn't say online, or hasn't played an online game. Who has not played an online game? Everybody's going, I ain't going to be the first one. What do you play, Abul?
I play For Honor and all that stuff, sir.
So basically, first-person shooter, RPG.
It's more like a fighting game, sir.
Okay. Alvarez, do you play? And if so, what?
Yes, sir. I play first-person shooters.
Okay. Bakken? You can say you don't play if you don't want to. It's no biggie.
I can't pick a single game.
Oh, so you're an eclectic. You play them all. Whatever floats your boat. Okay. Garcia, do you play? And if so, what? Same with Johnson's writing in there. And then, okay, FPS, first-person shooter and racing. Garcia? Yoo-hoo, Garcia. Okay, first-person shooter. Then we got Wagner. Do you play?
Yes, I play first-person shooter and open-world games.
Okay. James?
Play MMOs.
Hey, your mic went crazy on me.
I said I play MMOs.
Okay. Richards?
I play League of Legends, sir.
Okay, and Smith?
I play a lot of MOBAs, open worlds, and first-person shooters.
Okay. Like I told you, I play World of Tanks. So you can probably relate to this. The short-term jitter sometimes is ridiculous because, for an example, I'm in one of my tanks. I have this one particular place where there's a river on the left-hand side. I got to make a right-hand turn when I go around the rocks there to get to the river so I can set up where my defensive position is, or where I like to be. Well, all of a sudden, here comes the ping rate. It goes through the roof. I glitch. The next thing I know, I'm in the river drowned. You guys can pretty much relate to this when you're playing online and that ping rate just goes through the roof. What you just experienced is timing jitter. Didn't know that. Yeah, it just pisses you off to no end. Especially if you're doing a mission and this might be this might be the game. Because you can look at everybody and go, oh, I played that person, he sucks. I played that person, she sucks. Okay, that guy I'm going to have to watch out for. You know what I'm saying? So, there's a list of everybody from your team versus their team. And, if you think that you're going to have a great game and you got the perfect place and that ping rate goes through and just destroys everything. Sucks. Elastic Store, that's that buffer that you just experienced when you are trying to play a video, and that makes that little circle, and then down at the bottom of YouTube you'll see the buffer. You'll have a pale line and then the bold line. The bold line is the one that's actually playing the video, and sometimes that bold line will catch up with the faded line and then it'll stop. And then that little circle will come through and so forth and so on. Well, what you're doing is you're putting in an elastic store, and the computer isn't quite keeping up, or your internet is just not quite keeping up with it. So that's how it is able to remove that particular type of jitter. Just wish they would do it for the gaming aspect. When we have long-term jitter, that's a big thing. And that's because you have unsynchronized clocks, and even though they're extremely stable, you're going to lose synchronization. And the easiest way to explain that is there is a time delay when you send one message out, and let's just say you have a couple miles to get to the distant end. There's going to be a time delay of that clock versus the other clock. So what happens is they use something called phase-lock loop to sync up the incoming time with their time so everything can sync up. That's a whole idea behind this long-term jitter. It never corrects itself. It just helps with making everything synchronized. That's in most of your timing gear, like multiplexers, your SATCOM gear, your modems, everything, using this phase-lock loop. This is not a new term, by the way. This has been used since, good gosh, I want to say the early 40s and 50s. So it just gives you an idea of what's going on here. Network synchronization. We have 4 different types of network synchronization. We got plesiochronous, which I like to call the dinosaur. For your memory, you have mutual, master clock, and master slave. So let's go through each one of them. Plesiochronous, this is basically nodes. So in that way, you're using the elastic store to be able to talk to each other and get everything synced up. We also have mutual. This also has more nodes. The thing is, you're averaging everything. And if you lose one of these nodes, the others just re-average everything and sync back up. I like to classify this as your LAN party, when everybody's connected up and you're playing some games together. And if one person has had enough and they decide to leave, everybody's still synced up. We have master clock. This is what I like to equate to Big Ben in England, in London, England. If Big Ben fails, back in the day, the 1800s, then the whole area around there fails. They don't know what the accurate time is. Now, why was Big Ben there for a purpose? Well, back in those days when they built Big Ben, that was a time for all of London. And when it chimed, everybody knew what time it was. So they would set their clocks to that time. Now, nowadays, if you take a look at what's happening to Big Ben, you will find out that it is down now for refurbishing. It's pretty doggone old. It was built in the about the mid to late 1800s. Because that's when time was starting to come into sequence. Of course, when it fails, everything fails. Just to give you an example, what happened to me back in the day, 19 whatever. I'll leave that up to you to figure it out. But we had all of our clocks was synced to a master clock in the principal's office. When that clock failed, we did not know when to change our classes or when you were late and so forth and so on. So what they had to do is get over the intercom and let everybody know, hey, it's time to change class. You got 5 minutes to change class, and so forth and so on. Okay, everybody should be in the class. So that's how they compensated because of the master clock failing. Again, master clock fails, everything fails. Something called the master slave was what I like to call the pyramid effect. This is what DoD uses. If you lose the master clock, there's always one to take over. So basically your pyramid, like the pyramid scheme you hear about, well, this is one time the pyramid scheme actually works to people that are, to an advantage. And why is that? Well, our master clock is, let's just say, in the headquarters of Maryland, which is where our USNO is. Well, if that one goes, let's say somebody blows it up, at least we got a clock that's, back at Pensacola. They blow that one up. Well, we also have another clocks over, let's say in Randolph and Offutt, and the list is long and distinguished. So if we lose one, somebody's there to take over. So we've gone through
Redundancy.
Yes, redundancy. So that way, if something really does happen, we have a backup to the backup to the backup to the backup. So we have purpose of timing that we just went over, timing standards, timing sources, time distribution, and time coordination and distribution agencies, timing, jitter, network synchronization. Any questions?
No, sir.
All right, so let's go to the next one, because I know you guys are looking at the time going, oh, it's 10:48. Yes, we got a certain place to be. Does anybody have to go to the bathroom real quick?
Yes, sir.
All right, let's take 5 minutes. I have 10:48. Be back at 10:53. All right?
Yes, sir.
Unpause it. Get us in regular Discord, and we're going to look at identify basic facts of and state general principles associated with the principles, capabilities, and limitations of multiplexers. And as you well know, I told you earlier about the 28 questions you got to get right on the test. You can only miss 12 out of the 40 that you're going to go through. So look at multiplexers today. Hopefully this will be able to be explained to you well. We're going to go through general multiplexing terms, input data relationships, types of multiplexing, modes of TDM, demultiplexing and signaling formats, as well as analog to digital conversion. Without further ado, let's look at some terms here. First of all, we have analog and digital. Well, the way I like to look at analog digital, if you know one, then you know the other because it's the opposite. So I take analog for the first part of this. You have infinite number of values. You look at digital, it says limited. So you can say, well, the first two words there, you can say infinite or unlimited number of values for analog. Or you can have a word called indiscrete. That's an electronics term for unlimited and infinite. So now you know analog. Well, the opposite of analog is digital. So it's discrete, it's limited, it's finite. So there you go. That's an easy way of looking at it. And when we look at this, you can see an analog signal is all over the place. And then you have the digital, it's ones and zeros, so it's defined with, in this case, 0 to 5 volts. It's always defined. We have bit. Pretty much you guys went through block 6, identifying bits and IP addresses and so forth and so on. Ones and zeros. A bit, 8 bits makes a word. In some instances, there are 2 bits that can make a word. 3 bits of dollars, stand up and holler, all that kind of crap. You get the point. We have multiplexing. This is what's going to happen is we're going to take, I'm sure that you saw that picture at the front end of one alpha that showed the multiplexer with multiple users, and then it had single entities. So users and channels can be interchanged. However, channels are the amount of ports on the back of a multiplexer. If you only have 24 channels, you could probably have more than 24 users. It depends on what you're doing. But the bottom line here is we're going to combine all those channels into one stream coming out. It's going to go to the distant in that stream. It could have analog, it could have digital, it could have voice, data, video. Depends on what you need for it. And this gives you an idea using the picture of what's going to happen. You have 1, 2, and 3 as far as channels. You have number 1, which is the diagonal lines. You have 2, which is a solid bar, and then you have number 3, which is the horizontal lines. And you can see each one that comes out, it goes through channel 1 to channel 2 to channel 3 and rinse and repeat. And that's how we get our aggregate coming out. It's a single thing. And of course, this is happening extremely fast. Next up, we have sampling, not to be confused with the buffets around here. So what we do with sampling is when we look at the horizontal line, each of those sections that we're going to sample has X amount of time in it, and it's equal all the way through. So we're going to take a sample of each one of those waves to give you a sequential idea of what the analog waveform is going to look like in a digital world. Frames. This is how we identify and keep everything straight to where it is synchronized when it comes out. Because if you jumble all this information up, how are you going to know to the distant end, where's channel 1 going to go? Where's channel 2 going to go? But by creating a frame, what you're doing is you're going through all these channels and saying, hey, you're number 1. Here's your frame bit for number 1. Here's a frame bit for number 2, so forth and so on. And everything's in sequential order, so when you get it at the distant end, it knows where to put everything. Because nothing is worse, and I'm sure you guys have had this before, when you buy a brand new phone and you get a new number and you get somebody to call you that you have no idea who it is, and it ends up it's a wrong number. Oh, gee, that's synchronization for you. Then you have something called non-information bits. Non-information bits is not part of that 8-bit word. So you're going to send an 8-bit word to the distant end. Well, how's the distant end going to know what to do with that 8-bit word? Well, we have something called start bits. We have something called a framing bit. So framing bit's telling it where to go. Start bit says, hey, this is the beginning of the word. Stop bit says, hey, this is the end of the word. A stuffing bit is with another synchronization time where you're cramming stuff in it to make it synchronized. We'll get to that in just a minute. Next up, we have bandwidth. Now, this one is a term used often interchangeably with both the RF world and the computer world. So we have one where it can be a rate, like 56K, or a frequency range from, in our case, 300 megahertz to 3 gig. We have something called asynchronous. Now, this is where the multiplexer is going to send stuff out at irregular intervals. Now, what does that mean? Well, if you've got a multiplexer and you have, let's just say, 100 users on it, are all 100 users going to send data at the same time? Probably not. So what they do with asynchronous is, and they give another example like a keyboard or mouse. How often do you use the mouse or keyboard all at once? Well, they do have stop and start bits. But I like to use it for synchronization when you're sending it down the line. We'll get into that in just a minute. Synchronous means that every time, and I equate this to, because I like Lionel trains. If you have a Lionel train pull up to the depot, you have X amount of time to unload the boxcar and load the boxcar. And you have X amount of these that you've got to do. You have X amount of time to do it in. It's that way all the time, constantly going around and around and around, looping back. So you have, okay, here's frame 1 for channel 1, here's frame 2 for channel 1, and so forth and so on. So what you're doing is let's just say a second, you have a half a second to offload and a half a second to load. If there's nothing there to load or unload, you lose that time. You lose that time. So you have to wait till the train comes back around before you can load it up. Now, what works for synchronous may be things like I have a camera set up on my house, So that's constantly, that would be a synchronous way of looking things. Why? Because it's going to go each one of the channels. I got 16 cameras, so it's going to go through 16 equal times in looking at the picture that camera is going to represent. Then we have something called isochronous. Now this one is where it takes both the asynchronous at a synchronous rate. In other words, we have a flexible rate that is at a synchronous rate. Okay. The problem with this is that it is a ton of what's called overhead. Overhead is the non-information bits. That's another way of describing it. You will see this later. Also, I like to relate to isochronous. Anybody has seen Tron Legacy?
Yes, sir.
Okay.
Yes.
What was Korra?
And ISO.
There you go, ISO. And if you watch how she's developed, this is how they developed it. Crazy, ain't it? Next up, we have frequency division multiplexing. This one is where we are going to use the frequency and send out our data. This is the precursor to what you have today as far as your cell phones are concerned. Let's take a look. Your cell phones, at one point, back in the old days when you had a flip phone, will work off of frequency. And when you opened up your phone, that was its time to go, okay, I got to look for a cell site. So the cell site would say, hey, this frequency is open so you can use it. And then you would be able to talk to people as long as you would stay in one area, or if you got to a place where it was really weak, like in the, for example, if you came inside and it's really weak, well, guess what? You probably got dropped off. Normally, when you're going between cell sites, they have a computer to tell you to hand off. Well, the problem is if you are on, let's say, in their case, user A at 82 to 83, and you go to the next cell site and someone is using 82 to 83, more than likely you are going to get dropped. That's the bad part of frequency division multiplexing. Then we went to something called time division multiplexing. Well, this one is we look at the channels, which are basically frequencies again. And what makes it nice now is the computer can switch your channels as well as the timing in there. So if you happen to be on the same channel as, let's say, two others, you're still having multiplexing time to where you're being able to, talk back and forth. Now, it's got faster, it's got better, so we don't experience very many drops anymore. That used to be a big thing back in the day. Hey, we don't drop you. Bull crap. It just goes to show you how we've gone upscale in technology. This gives you a basic understanding of what they call interleaving. And you see we have frame 1, frame 2, frame 3, frame 4. You'll see that each one of these numbers can get jumbled up. Not jumbled up, but you can see that all these numbers are in sequence. I made a mistake there. Each one of these numbers are in sequence with each of the frames. The idea is when you get to the next end, to the distant end, each frame says, hey, this is frame 1. This is the first. This is where channel 1 goes, this is where channel 2 goes, this is where channel 3 and 4 and so forth and so on. Most of our multiplexers, though, do have a lot of channels to them. Normally the standard's about 24 channels, so it would be really long if we had more than 4 channels in there right now. But this gives you a basic understanding of how we interleave the frames in there, and you're going, okay, take it with a grain of salt, right? Yeah, pretty much so. Interleaving is considered a form of forward error correction, and that's going to happen in 3 Bravo, which is another day. We have synchronous and asynchronous for modes of TDM. We're just going to briefly go through this. Synchronous does have frame bits, and it is, in some cases, a lot of wasted bandwidth. You don't have to have a start and stop bit, but there are other pieces of overhead that's got to go with it, like a frame bit and a synchronization bit and a couple other things that go with it. Here is what you have for synchronous. You can see that we first start off with a frame bit telling everything where it needs to go. You have Alpha, Bravo, Charlie, and Delta. If you take a look at the left-hand side, you can see Alpha, Bravo, and Charlie and Delta are in line. You go to frame 2, look what's missing. Well, we have no Charlie. Well, that's wasted bandwidth. When we go to frame 3, you can see that we have Alpha and Delta, and of course, Bravo and Charlie's not there, so that's wasted. It's wasted bandwidth. And then lastly, with frame 4, you can see that on the left-hand side of the TDM, there is nothing other than Alpha, and then it's still got to have the time to do Bravo, Charlie, and Delta. Again, wasted bandwidth. Now, if you're running cameras like I am, that's a great example of synchronous TDM where you're not losing your bandwidth there or wasting it. When we look at async, this one is where we have our stop and stop bits along with everything else. The big thing is you're going to have what's called multiplexer efficiency, but I'll get to that in just a minute. You can see the async, it's the same scenario as sync. The difference is now you're not having to waste the bandwidth for areas that do not have any information to put in. So when it gets to frame 2, you can say that it's getting quicker to get to frame 3, and it gets even more quicker to get to frame 4, and so forth and so on. So if you don't have any information in there, it's blazing speed. So I'm guessing that most of you are on Boingo or have had Boingo at one point. And with Boingo, you'll notice that there is a lot of problems with it. You're trying to get on. It takes time for you to get on. Well, let me try to explain this because computers are asynchronous. The problem is when you have everybody wanting to get on, you're going to have difficulties in that TDM phase in trying to be able to squeeze into one of those timing sequences. And that's to watch your movies or, when you're playing an online game. But when you get late into the night, let's say 1, 2 o'clock in the morning, there's not as many people up playing games at that point. So pretty soon you're able to play online without too much of a problem. That's because of this. Asynchronous has said, hey, we don't have as many people on there, so now you can do what you want to do with it. Or real early in the morning. There you go. So it's a very flexible way of doing TDM. Now this one's called isochronous. It doesn't have the actual stuff in there, but you have stop-start bits just like asynchronous, but there is this thing called synchronous timing. So if you don't use it, you gotta cram some stuffing bits into it. And if you look at frame 2, we're missing Charlie out of there, so something's got to happen. The way it works is the stuffing bits now come into play, and that's to make sure that your particular time does not get out of sync. Kind of crazy, I know. Demultiplexing, if you do it in multiplexing, you got to do it in demultiplexing. What does that mean? If you encrypt your messages, then the distant end has to decrypt them. In other words, demultiplex them. So that's the big problem here. If you're doing something in multiplexing and it doesn't do it in demultiplexing, why are you even doing it? So you got to make sure both ends are doing what they're supposed to be doing. Next up, we have signaling formats. For signaling formats, we're done and we can go and get something to eat. There are 3 different types that we go through. One is NRZ, non-return to 0. Second one is return to 0, and then the last one is called condition die phase. These are 1s and 0s. You're going to see that there are some differences between each one of these signaling formats. You are going to see these when you get to the NSM lab. Let's go through them. Now, the first one is I always like to ask you, when you're reading this number, how do you read it? Right to left, left to right. You're going, I don't know. Abul, how do you read it?
Left to right.
Alvarez?
I read it right to left.
How do you read it, Bakken?
Left or right, same.
Garcia? Write it, and Johnson's writing it?
Left to right.
Okay. Wagner?
My brain processes it right to left, but I say it out loud left to right.
Okay. James?
Left to right.
And Richards?
Left to right.
And Smith.
Left to right.
Okay. Consensus is left to right. Everybody reads from left to right. But numbers always start from the right to left. Okay? Because when I read this number, and it's a habit, because everybody's trained to read from left to right. Well, what you do is you look at that first number and then you count everything over. Well, like Wagner said, my brain processes it from right to left, but I read it from left to right. That's exactly the scenario that we're seeing today. So with electronics, and you're going to see the problems that we have, especially in the AETC world of trying to get you guys to think the correct way. And we're human too. But when you do numbers, it's always from right to left, but the habit is from left to right. So I just wanted to point that out, that everybody does this. And I've been trying to get Dolan Hall to get them on the same page, but it never works. But now we have something here. You're going to notice that most of our products, notice I said most of our products, are going to track from the right to left when we talk about signaling formats, words, 8-bit words. Most of our signals should be from right to left. And if you really truly looked at what a signal generator is doing, it will track from right to left. There are pieces of equipment that track from right or from left to right, like the spec ante, and that has everything to do with the way it's set up and how the habit turned out. But numbers, period, right to left. I just wanted to point that out, because when you see what's coming up on our signaling format, it will have some bearing on it. 8-bit words. Again, you have 8 different logics going from 1, 2, 4, 8, 16, 32, 64 to 128. Again, when it comes out, it's going to spew out the first one going from left to right, the number 1. The next line would be a number 2. A number 3, a number 4, number 5, number 6, number 7, number 8. So when you look at this, it will be in accordance with the way the numbers are going. So we're going to look at NRZ. NRZ is the most common one out there as far as what is internal. Notice that word, internal to a multiplexer. So I'm going to try to give you a picture by painting it through my words. You like that? Painting it with my words? No?
Yes, sir.
Bad. No one has a pun for the day? Good grief. Anyway, it is the most common format within a multiplexer. the way a multiplexer works, so let's just say we got a 24 channel multiplexer. Not all users will have the same format. So when it comes into the multiplexer, it could be, good grief, got a big mosquito in here. Sorry about that. And it nailed me. The big thing is the users may have different formats, but when it comes into the multiplexer is going to change those formats into NRZ. While at the same time, when it's changing it, it's looking at the clock that the distant in is sending it and using that line clock to sync everything back up into a aggregate, and then when it sends it to the distant in, it could be any one number of a different formats. Most formats I've seen that sends out is normally either CDI or NRZ. And that's sending it to the distant in, not receiving it. Receiving it, that's the users that have the different data. Normally, back in the day, we would have to program the cards to the signaling format, but nowadays it is nothing more than plug and play. We're going to go through two different types of NRZ, neutral and polar. Now, pay attention to the word non-return to 0. That's that phrase, but the big word is non-return to 0. What does that mean? Halfway through the clock cycle, it's supposed to do something if I want it to be timed perfectly. Well, in our case, it doesn't. Let's take a look. Neutral is the first one we're going to look at. It's from 0 to 5. Normally 5 is a logic of 1 and 0 is a logic of 0. You'll notice it says that last sentence requires a separate clock to stay in sync with the demultiplexer, and it's not self-clocking. Here's what the format looks like. We're going from the right to the left. You can see that most of our clock cycles, we always start in the positive. This one goes up, goes back down. Since it is a data of 0, it does absolutely nothing. Stays 0. When we have another piece of data of 1, halfway through the clock cycle, it does not return to 0, hence the word non-return to 0. We have another data of 1. Again, it stays at 1. It doesn't return to 0 halfway through the clock cycle. Now we see 3 zeros in a row. It's going to stay 0. We see another piece of data that comes in that's a 1. We're going to go to the plus 5 halfway through the clock cycle. Nothing happens, so it stays a 1. It sees a 0 come in, so it's going to go down to 0. It stays there. We have another piece of data of 1 that comes in, goes to a plus 5. And then another data of 0, it goes to 0. So nothing happens halfway through the clock cycle. So that's telling us it is not self-clocking. And what does that mean if it was clocking? Well, that means I don't have to send the clock cycle alongside of the actual data. So in this case, I have to send the signal format, NRZ, with a clock cycle so I can tell the distant in, this is the way this thing syncs up. The signal format represents our data of 1s and 0s. Let's look at polar. The only difference between polar and neutral is 5 volt difference of potential versus 10 volt difference of potential. The only nice thing is okay, I can go further with polar. Again, it's not self-clocking. Looks almost identical to the NRZ neutral. The difference is you have a 10 volt difference of potential and not a 5. That's it. Again, you're still sending the clock cycle with it. The data represents, or the signal format represents the data. Return to 0. There were 4 different types. Notice that name. It doesn't have the non in front of it. It's return to 0. 4 different types: neutral, polar, bipolar, and then bipolar with zero suppression. Take a look at these. Neutral means that halfway through the clock cycle, if I'm at, oh, I got you, little rascal. Ooh, God, lots of blood. Sorry about that. Ew. If you're squeamish. So we have the RZ neutral, which halfway through the clock cycle, you're going to see something. Hence the word return to zero. But again, it's only +5 as a 1 and 0 for zeros. Those are the logics. Again, it's not self-clocking. So let's take a look. You have 0, stays 0. You have 2 1s in a row. And notice what happens halfway through the clock cycle. It returns to 0. You have 2 1s in a row, it returns to 0. It's actually making it look like it does something every clock cycle. But the problem is when you have a 0, there's nothing in there to help it out to say, hey, I gotta have a clock. I now need a clock cycle to be sent with it. So this particular one is not self-clocking. It is pretty much identical to the NRZ one that we showed you in neutral. The difference is how anytime we see a logic of 1, there's something happening halfway through the clock cycle. Next up, we have a RZ polar. This one, we have a logic of 1 is a +5. A logic of 0 is a -5. So there are some differences. Look at that last sentence there, or words. It is self-clocking. And you're going to see why, how easy it is to identify that this one is self-clocking. Look what's happening. So the clock cycle goes, in this case, we have a data of 1. We're going to go to a -5. And then halfway through the clock cycle, you can see at the top, halfway through the clock cycle, it's going to go to 0. Hence the word return to 0 halfway through the clock cycle. We have a data of 1. This one's going to go to a +5 halfway through the clock cycle. It goes back down to 0. Hence the word return to 0. Then we have another data of 1. This one's going to go to the +5. Go back down to 0 halfway through the clock cycle. Then we have 3 zeros in a row, and you can see that where we are going to the -5 halfway through the clock cycle, we go back to 0. So you can see that this is pretty solid evidence that this is self-clocking. So you don't need to send the extra information of the clock with it. So that's less information you got to send, and this can be pretty doggone fast. Next up, we have something called RZ bipolar. Bipolar meaning it's flip-flopping from one side to the other. Logic 1s are either a +5 or -5. Logic 0s are always 0. This one is not self-clocking. However, you can make it self-clocking with what's called zero suppression. Interesting, eh? This is what the RZ bipolar waveform looks like. So you have 0, and like we said before, the 0 stays 0. You have a +1 or a data of 1. It's going to go to +5 because we always like to go to the positive side first in electronics. And then halfway through the clock cycle, we go back down to 0. Hence the word return to 0. The next data of 1 flip-flops. In other words, it goes opposite of the last one. In our case, another data of 1 will go to the -5. We go 3 zeros, it stays 0, and then we get to a 1 again, data of 1. It's going to go to the +5 because it's looking back and saying, oh, geez, I was at a -5, now I need to go to a +5. So we get another 0, it stays 0, and then, of course, we get another data of 1, and it's going to go down to the -5. And then back up halfway through the clock cycle. So you can see why this would not be self-clocking. The next one, which is RZ bipolar with zero suppression. Now I'm going to warn you ahead of time. In the NSM, you're going to see this named a different way. It is alternate mark inversion. Get it? Alternate mark, meaning every time it needs to flip-flop, it works just like bipolar. With bipolar with zero suppression, you're going to see terms like B8ZS, in other words, Bravo 8, Delta, no, it is Bravo 8, Zulu Sierra. You're going to see terms like Hotel Delta Bravo 3. These are all self-clocking, by the way. Bravo 6 Zulu Sierra is T2. So you can see that each one of these you're going to see in the NSM as self-clocking. RZ bipolar has something called a bit violation. What does that mean? It means that that bit is not going to be what you think it's going to be, but that's where it's going to sync up or tell the dissonant, hey, I threw a bit violation in there, so we have to sync up. Like, okay, dissonant knows it. It doesn't need a clock cycle to go with it. Here's what bipolar with zero suppression looks like. In our case, it emulates pretty much what bipolar was at the start. So you have two pieces of data of ones, and they flip-flop. Here's where it gets kind of weird. This one is saying at the fourth zero, we're going to throw what's called a bit violation. Well, that's to make sure that we do have the signaling format self-clocking. By throwing a bit violation, it's number one, you're generating it at the transmit side, and the receive side at the dissonant will know, oh, okay, you just had 4 zeros in a row. Why? Because I got a bit violation on the fourth one. Bit violation meaning that it will emulate whatever the last data of 1 was in our case. In looking at this, well, the last data of 1, it was at a -5. So if it was going to be a regular data of 1 coming in on that fourth zero, it would be a +5. But that's not the case. It's saying to the dissonant, hey, I just had 3 zeros in a row. The fourth zero is a bit violation. Oh, okay, so I'm going to sync back up then. And then, of course, it goes back to the regular stage of, here's a data of 1 and it flip-flops like it was supposed to. And that's how we get self-clocking out of RZ bipolar with zero suppression, or better known as alternate mark inversion. And there's two different styles of alternate mark inversion. One is the bipolar. The other one's alternate mark inversion with suppression is what it will say. That's going to let you know. So we've covered the first two sets of formats, which is non-return to zero. None of those are self-clocking. We've looked at return to zero. We got RZ polar that's self-clocking, and RZ bipolar with self-clocking. And then the third one is called conditioned diphase, which is self-clocking. So those are your 3 self-clocking signaling formats. The big thing about conditioned diphase, if you were to look this up on the internet, you will find something called differential diphase. That's the name of it. It's explaining conditioned diphase. The military just likes to change the words. It is going to use something called transitions. It's not going to use the, hey, a +5 is 1 and a 0 is a 0. Okay, that's not how they're going to do the logics. This one relies on transitions. How many transitions happen within a clock cycle when you have a 1? That's a data of 1. You're only going to have 1 transition. When you have a data of 0, there are 2 transitions. It doesn't matter if it goes from 0 to 5 and 5 to 0, or from 5 to 0 to back up to 5. So those are 2 transitions that it could be, either one. Same with the logic 1. It's either going to go from 0 to to a 5 or a 5 to a 0. Again, this is self-clocking. Let's take a look. Starting from right to left, you can see that we have first data was a 0. We're going to have 2 transitions. These transitions are going to happen within the clock cycle. So the first time a clock kicks in, that's your first transition. The second transition is when the clock cycle changes. That's how it's self-clocking. The 1, most of the time, will always be on the leading edge. It is very possible that the 1 could be somewhere in between all of that. But it's only when the zeros come into play that it syncs back up. So that's the way it's able to identify for being self-clocking. So you can see every place where it has a 0, you have 2 transitions. Every place that it has a data of 1, there's only 1 transition. Most of the time, the data of 1 always gets with the leading edge of the clock cycle. Lot to digest, eh?
Yes, sir.
All right. I got 11:30, and I'm getting hungry. I'm sure you guys are getting hungry. We are coming up
Yes, sir.
to the analog to digital conversion. We're going to stop right here, pick it right back up at the 1 o'clock, and we're probably going to go for about another hour and a half on it. So you guys have a wonderful lunch. We'll see you at 1 o'clock, okay?